Hey everyone, welcome to the lecture for section 3.1. It's integration by parts today. So integration by parts is really just the reverse or the undoing of the product rule. So if we just think really quickly about our calculus 1 days, if we wanted to differentiate the product of two functions, so let's say we wanted to take f of x times g of x. Its derivative would be f prime of x times g of x plus f of x times g prime of x. And so if I integrated this, because integration is linear, meaning if I integrate over a sum, I can just take the sum of the integrals. So if I integrate both sides, then what I would have is right, so of course there are dx's in here, but just for simplicity's sake, so just integrating everything. Then what I would have is f of x times g of x equals the integral of f prime of x g of x plus f of x times g prime of x. And you're probably wondering, like, well, how is that helpful? Well, in the case where we have integration by parts, if we're kind of just looking towards this, think of u and v as f and g. So if I wanted to take, if I just rearrange this a little bit, I'm going to get f of x times g prime of x. This equals f of x times g of x minus the integral f prime of x times g of x. So really what I'm looking at in terms of u and v, which is usually how we express integration by parts. So this is the integral of u, the derivative of some other function. It equals the two original functions minus the integral. So this is really du, and this is v, right? So we're thinking about u equaling f of x and v equaling g of x. So this is where the formula for integration by parts comes from. It's just looking at the product rule and then kind of undoing it. So how do we undo differentiation? We use integration. And so that all comes from there. So let's go ahead and try it. In this first example, they're telling us specifically what we should use for u and for dv, right? So notice that you're looking here at u and dv. So when you do integration by parts, you want to say, okay, one of these functions is u, and the other one is the derivative of a second function v. So they're telling us let u equal x and let dv equal sine of x dx, right? So that comes from here, and the other one comes from here. So if u is x, then I know that du, the derivative of u, is just going to be 1 dx. So I'll just write dx. And then for v, I want to integrate sine of x dx. So I'm going to get negative cosine of x. And so now that I have my u, my v, my du, and my dv all set up, I'm ready to apply the formula for integration by parts. So what we'll end up with is the integral of x sine x dx, this has to equal u times v. So that's x times negative cosine x minus the integral of v times du. So that's just going to be negative cosine x dx. And so I can go ahead and simplify these double negatives. So I get negative x cosine x plus the integral cosine x dx. And we know the integral of cosine x dx is just going to be sine of x. So we get negative x cosine x plus sine x, and don't you dare forget that integration constant. So negative x cosine x plus sine of x plus c. And so that's going to be our integral. And it's nice that they gave us what u and v should be, but in general, we don't have this information available to us. We kind of just get the integral and we're like, okay, I have to choose what is u and what is dv. The good news about that is that there's only two ways to do that. So if you choose wrong, you'll know it right away. Because what will happen is your integral will get worse. It'll get more complicated. But you don't have to rely on just chance. There is a mechanism or a mnemonic that people use a lot. So one of them is ILATE. You may have heard that before, but really it's just I-L-A-T-E. So this stands for inverse trig. That's your I. Your L is logarithms. Your A is algebraic. T stands for trig. And E stands for exponential. So what that means is that, first of all, you're in charge of knowing what these functions are and what they look like in their basic form. But what it means when you're choosing your functions, if you have, so we'll set it up for this problem specifically. You want to go through and identify. So we have two functions in our integral. We have x and we have sine of x. So sine of x is a trig function. So that goes here. X is just algebraic. So when you write this list vertically, the first one to appear closest to the top, that's your u. And then the one that's further down, that's going to be your dv. So that's where we get sine of x dx equals dv. So that's how this ILATE, or in the book they use LIATE. In truth, the I and the L are interchangeable, and the T and the E are interchangeable. Kind of like an order of operations, you could do division and multiplication, or multiplication then division. They're grouped together. But PEMDAS is the mnemonic that we're all familiar with. ILATE is the mnemonic I'm familiar with, but you could switch it up however you want with respect to IL and TE groupings. So let's see if we can use this ILATE mnemonic to determine the integral given here. So the first thing I would do is I would make my list. So I would say, okay, if I have I, L, A, T, and E. So I have two functions. I've got ln of x and 1 over x cubed. So ln of x is obviously logarithmic. So this is going to be ln of x. And then 1 over x cubed is going to be algebraic. So that means I'm going to use ln of x for my u and my algebraic function for my dv. So if I set that up, let's let u equal ln of x, and we'll let dv equal 1 over x cubed dx. So I'm going to have to integrate to get v, and I'm going to have to differentiate to get du. So the derivative of ln of x is 1 over x dx. And the antiderivative of x to the negative 3 should be something to the negative 2, right? So we're going to get something over x squared, but we're expecting a constant, right? So this should be kind of compensating for that constant. So if I took the derivative of that, I would get 1 over x cubed. So now I'm in business, and we can go ahead and set up our integral. So we have ln of x over x cubed dx. So this equals uv minus v du. So u times v is negative 1 over 2x squared times ln of x. That's the product of u and v. And then I'm going to subtract off the integral of v times du. So I'm going to get negative 1 over 2x cubed dx. And this is another really straightforward integration. So I'm just going to rewrite the first bit, negative 1 over 2x squared, ln of x, and then the integral. So this becomes a plus sign here. So maybe I'll write out that intermediate step, 1 over 2x cubed dx. Okay, so for then my last step, I'm going to get negative 1 over 4x squared plus c. I could leave it like that, or I could go ahead and combine the signs. So negative 1 2x squared ln of x minus 1 over 4x squared plus c. Not all integration by parts are this easy. Sometimes you're going to have to use it multiple times. So I want to go back up to the first example really quickly. Notice that our u was the function x. And anytime we have a polynomial, like I know that if I differentiate a polynomial enough times, eventually it will become 0, right? So if I have a 5th degree polynomial, its first derivative is 4th degree, its second derivative is 3rd, then to 2nd, then the 1st degree, then it's constant. And if I differentiate a constant, it'll be 0. So that's kind of the idea that's in play here as well. So to me, just from experience, I already know that I'm going to have to use IDP 2 times here. And I'll show you a trick at the end of this problem. We'll do it straightforward, then I'll show you this cool tabular method. So for us, we have x squared, and we have e to the 3x. So this one is algebraic, and this guy is exponential. So in the world of Hilate, we know that x squared comes before e to the 3x. So that tells me that this is going to be my u, and this is going to be my dv. So I'm going to let u equal x squared, so that du equals 2x dx. Then I'm going to let dv equal e to the 3x dx, so that v equals 1/3 e to the 3x. And then I'm just going to go about integration by parts using my formula. So x squared times e to the 3x dx equals uv, which is 1/3 x squared e to the 3x, just u and v multiplied together. Then I'm going to subtract the integral of v du. But here we can see that we're kind of back to where we started. We're in a bit better shape, but I still have this product of two functions. Before, we've seen the product of two functions, and it was a U substitution. But in those cases where we had a U sub, one function was the derivative of the other. We don't have that. So that's another tip off that you're going to do integration by parts, by the way. So let's hit it again. It's the same thing. X is algebraic, e to the 3x is exponential, so it's still going to be the same thing. So we're going to let u be 2/3 x so that du is 2/3 dx. And then we're going to let dv equal e to the 3x dx so that v is again equal to 1/3 e to the 3x. So now just kind of writing this whole thing from beginning again, we have x squared e to the 3x dx. I still have my first part. That doesn't go anywhere. But now I'm going to subtract this whole thing. So this integral here is going to be this guy over here. So I get uv, which is going to be 2/9 x e to the 3x minus the integral of v du, which is 1/3 e to the 3x, and du is 2/3 dx. So this will give me 2/9 e to the 3x. And now I'm feeling good because what's happening now is I know that once I integrate e to the 3x, I'm not going to be left, like I can just do that. I'm not going to be left with another integral. Everything's going to come out. And I'll be nearly finished at that point. So finishing this up, I get 1/3 x squared e to the 3x minus 2/9 x e to the 3x minus, so I'm minusing a minus, so this is going to become plus. So 2/27 e to the 3x plus c. So that's using integration by parts 2 times. There's another kind of fun way to do this. So a fun method deserves a fun color, I suppose. Sure. So we have something called the tabular method, and this is really cool. So like imagine if our integral here was like x to the 5th. We would have to do this process 5 times, and it would keep nesting and getting bigger and longer and awful. So tabular method is great for those instances, and the idea is that you want to pick your u as something that eventually differentiates to 0. You know, like a polynomial. And then du is just the other guy. So you have u, dv, and then you have a plus minus situation over here. So you create a table I'm not sure how much you need. So if u for us is x squared, then you just go down the column and you take its derivative. So you're going to have 2x, then you're going to have 2, then you're just going to have 0 and 0. I mean, I don't have to do that last row, but I already drew it, so hey. dv is e to the 3x, right? It's the other guy. So I get 1/3 e to the 3x. Now I'm just taking antiderivative, then antiderivative, then antiderivative. So then I get 1/9 e to the 3x, then I get 1/27 e to the 3x. And I already know I'm not going to need this, but if I were to do it again, I would get 1/81 e to the 3x. Then you start your plus minus column, and it always starts positive. So positive, minus, positive, minus, positive. Okay. So cool. What are we going to do with this table? We're just going to kind of follow a path. So the idea is that you go here, here, and then dip down. So what does this mean for us? It means we get positive 1/3 x squared e to the 3x. We've seen this. It's right here. The next guy, we go down. Now we're negative. So we're going to kind of cross over this diagonal, and we're going to come out over here. So we get negative 2/9 x e to the 3x. But that looks familiar too, right? Because that is this guy right here. And then we just repeat until we hit our zeros. So coming over, crossing down, multiplying these two things together and including the plus or minus. So I get 2/27 e to the 3x. And notice, well, okay, sorry, not the plus c, right? But notice that that's this. And then if I were to go to the next line, it's just 0. So once you hit 0, you don't need to go any further because every subsequent differentiation of u after 0 will also be 0. So basically you just add all these up. And then that's your answer, right? So you just add up all these terms, slap on an integration constant, et voila. So that's the tabular method. You're welcome to use it. If you never use it, that's also fine. If you plan on taking your actuarial exam, definitely know the tabular method. So let's see another instance of applying integration by parts more than once. This one is like not as obvious. So for this one, it's a composition of functions, but it looks like just one piece, right? Like so you have sine of ln of x, that's one function. It's not sine of x times ln of x, it's a composition. And our other function is really just, well, it's not there, right? But we could think of it as 1. So if I were to look at it like this, I could say, okay, maybe this is sine of ln of x times 1 dx, right? So multiplying it by 1 doesn't change its value. And this is exactly what we want to do. So if we were sorry, turning my page. So now you want to think again about this ILATE thing. So you have ILATE. And 1 is definitely algebraic. It's just a constant polynomial or a degree 0 polynomial. But where does sine of ln of x fit in? Is that going to be trigonometric, or is that going to be logarithmic? So let's make the wrong choice first, just to eliminate. So you might think, what is u and what is dv? So if we let u equal 1, we might be thinking like, okay, it's algebraic and sine is trigonometric. Well, then du equals 0. And if dv equals sine of ln of x dx, then to say what v is to solve the problem that we were given, because I need to find the antiderivative of sine of ln of x. So yeah, I definitely don't know what that is. That's why they're asking me, because it's hard. So this was not the right choice. And that's fine. And like I said, you'll discover really quickly whether or not you've created the right setup. Okay, so our only other option is the other guy. So let's let u equal sine of ln of x. Then we can compute du using the chain rule, and dv is just going to equal 1 times dx, so that v becomes just x. So the derivative of sine of ln of x is going to be cosine of ln of x times the derivative of ln of x, which is 1 over x. So now I'm ready to go ahead and integrate. So, okay, here we are. So sine ln x dx, this equals uv, so x sine ln x minus the integral of v du. So what's cool about this is notice that when I multiply v by du, the x's are going to cancel out. So I'm just going to end up with cosine of ln of x. And it's not great because we're kind of right back to where we started, but that's okay. So we're just going to do integration by parts again. So here we're going to let u equal cosine of ln of x. And we're going to let dv equal dx as we did before, so that v just equals x. And then this is going to be negative sine ln of x over x. And so this is the same kind of iterative process. So I'm still going to get my beginning stuff, so x sine ln of x minus the blue guy. So that's going to be uv, which is x cosine ln x, minus the integral of v du. And again, the x's cancel out. So I'm left with negative sine of ln of x dx. All right, so now here's the part that is, I think, very cool. So I'm just going to go ahead and just push that negative through and kind of simplify things a little bit. So I get sine of ln of x dx equals x sine ln of x minus x cosine ln of x, and then minus, because I have 3 negative signs, 1, 2, 3, minus the integral of sine of ln of x dx. But this is nice because look, these are exactly the same. Exactly the same. So I'm just going to add this, my sine ln x to the right. So I'm going to get sine of ln of x dx plus another sine of ln of x dx, right? So that was like 2 twins. And then this still equals just x sine ln of x minus x cosine of ln of x All right, well, if I have 2 of something, then I might as well just write that as 2 times that something. So 2 sine ln x. It's a good thing this doesn't have like a bunch of parentheses and characters and doesn't take forever to write. Geez. Oh, okay. Times x sine ln x minus x cosine ln x. Ah. So cool. I want to solve for integral sine ln x. So I'm just going to divide everything by 2. So okay, so that's it. So I want to integrate. All I did was divide by 2 in that last step, and then I slap on my constant of integration, and that's it. It's a bit long, but nothing crazy challenging. I think the hardest part of this problem is choosing your values for u and dv. But again, like I said, like when it comes to integration by parts, and in fact, when it comes to integration by parts and u substitution, it's pretty obvious right away if you've chosen your u correctly. And expect to make bad choices at times and just be okay with that. Like just pad that into your timing. Like I'm going to choose the wrong u eventually. But that's good news when you do that, because that means, okay, well, the next choice I make, I know is going to be right. So we also have the ability to use integration by parts on definite integrals, and it's exactly what you think it would be. You just evaluate it per the fundamental theorem of calculus part 2, using your limits of integration. So nothing super exciting there. So let's give it a whirl here. This is another kind of funky little integration. So it kind of, again, looks like we just have one function, right? So the idea is that you just want to integrate from 0 to 1 of arctan x dx. So this is another case where you're going to have that 1, that like stealth mode 1 in there. So if you go through and do your IL8, not that IL8 is foolproof, but it's helpful most of the time. So for us, arctan, well, first of all, 1 is algebraic. That's the easy guy. For arctan, that's an inverse trig, and that's the I. I stands for inverse trig. So this is going to be our arctan of x. So in that way, we can get our u. So this will be our u, and this will be our dv. So if we let u equal I guess I should stay consistent with my notation. If I let u equal arctan of x, and then I let dv equal 1 times dx, then v is the easy guy, it's just x. And the derivative of arctan, I hope you guys remember this from Calculus 1, it's 1 over 1 plus x squared. If that doesn't feel familiar, get on that immediately, or just like write it down, get a tattoo, something. All right, so let's set this up. So we're going to integrate 0 to 1 arctan of x dx. So we get u times v. So this is x arctan x evaluated from 0 to 1. And we'll do the evaluation at the very last step. Then I'm going to subtract off the integral from 0 to 1 of v times du. So that's x over 1 plus x squared dx. Oi. So now this integral is looking not great, but it should jump out to you that this is going to be a u substitution. So just a quick little aside. So this is a u sub. So we have to, like, I know that x dx is that derivative pair with 1 plus x squared. So if I let u equal 1 plus x squared, then du will be 2x dx. I don't have a 2x, so I'm going to say that 1/2 du equals x dx, because I do have an x dx. And then I'm going to change my limits of integration. So when x is 0, u is 1 plus 0, so that's just 1. And then when x is 1, u will be 1 plus 1 squared, which is 2. So now what I'm getting is x arctan x. These limits of integration didn't change because I'm not messing with this guy. He's already done. I just need to evaluate. I will, I promise. My integral, though, these limits have changed. Because I did my u substitution, they will now be from 1 to 2. And I'm going to get 1 over 2 u du. And this is a nice integral because I recognize it right away as the natural log. So I get x arctan x, again, for my original limits of integration, then minus 1/2 ln u, evaluating it from 1 to 2. So now that I'm here, I can go ahead and kind of just plug and chug. So this is going to be 1 times arctan of 1 minus 0 times arctan of 0 minus 1/2 of ln 2 minus ln 1. So I can go ahead and simplify a lot of this. This is just arctan of 1. This guy is 0. This guy is 0. So minus 1/2 ln 2. I'm not going to simplify natural log of 2 because I can't. I would just get a decimal approximation. So fine. U shall be the natural log of 2. And arctan of 1 is pi/4. So I get pi/4 minus 1/2 by the natural log of 2. If you are getting stuck on inverse trig evaluation, like if I said, you know, what's arc cosine of 1? Like we need to, those are the things that, those are little skills that you need to refresh on. If you get stuck and need a resource, shoot me an email and I can point you in a good direction. Or you could always drop into my office hours. But that's it, sorry. Did I finish that up? Yes. We integrated, we evaluated, and we're done. Okay, this is our last example. It's very exciting. So it looks like just a regular volume of revolution, but you'll see once we set up our integral for the volume, it's going to be a little hinky. F of x equals e to the x. So check this out. So f of x equals e to the x is this guy here. Okay, no, it's not. That was a lie. It should be asymptotically approaching the x-axis. Right, so it goes like that. So for us, I want to take this from 0, x equals 0, to x equals 1. So my region is here. So let's just think about this really quickly. If let's say I did a shell. Let's draw this a little bit more saturated. So you could draw a shell or you could do a disc. So if you were to do a disc, your disc, and we're going about the y-axis, by the way. So your disc would look like this, right? So for your disc method, you're going to have the integral from 0 to 1 of pi times g of y squared dy. So because we have that y equals e to the negative x, then we know that ln of y equals negative x, and then so x equals negative ln of y. So, okay, fine. So we have pi. If I square that, the negative becomes positive, but then I just have ln of y squared dy. And now I'm really a bit stuck. So you probably could do, so this is an example of like just exploring the problem. I don't know where this is going to end up. It's so exciting. So if u was, let's say, ln of y squared, then du would be 2 ln y over y dy. And then you could have dv equal to 1 dx, and then d would just, y. Okay, so then you'd have y ln y squared minus the integral of 2 ln y. But like, okay, haha, yes, see, good. So then what would happen? So then you would have 0 to 1 pi of ln y squared dy. And so you would get u times v, which is y ln y squared, minus the integral of 2 ln y dy. And all this is going from 0 to 1, by the way. Okay, so what's the integral of the natural log of y? You could definitely do it that way. I would have to look at a table to reference that, or kind of like Google search it. So this isn't really what they're after in this problem. Let's look at the shell method really quick. So if we look at the shell method, what we would end up with is shells like this, and then they come around, very exciting. And so the shell method would give us the integral from 0 to 1 of 2 pi x times the height of this shell, which is just e to the negative x. And this to me is looking a lot better, because I have like this very obvious setup. Like I know that e to the negative x is my exponential. And 2 pi x is going to be my algebraic. So I feel more in my comfort zone here. Again, you could do it either way you want to do. If you ever want to reference the example in the book, it follows the shell method. So 2 ways you can do this. You could pull the 2 pi out and slap it on at the end. Or you could let 2 pi x be your algebraic function. It doesn't matter. I'm going to go ahead and let u equal 2 pi x. So that du becomes 2 pi dx. And then also dv being e to the negative x is super easy to integrate. We just get that v equals negative e to the negative x. Nope, just kidding, just that, just by yourself. So now I'm going to go ahead and integrate, so I get 0 to 1, 2 pi x e to the negative x dx equals u times v, which is negative 2 pi x e to the negative x, minus the, from 0 to 1, minus the integral, also from 0 to 1, of v times du. So this is going to be negative 2 pi e to the negative x dx. I'm not going to bother with canceling out that double negative because, well, you'll see when we integrate, it takes care of itself. So I get negative 2 pi x e to the negative x, evaluating from 0 to 1, minus 2 pi e to the negative x from 0 to 1. So now I really am going to pull out this negative 2 pi. So when x is 1, I get 1 e to the negative 1, and then when x is 0, 0 e to the 0, minus 2 pi e to the negative 1 minus e to the 0. So we can go ahead and simplify all this. So negative 2 pi, this guy dies. So that's just 1 over e. And then I get minus 2 pi times 1 over e plus 2 pi, right? So that double negative there, and e to the 0 is just 1. So I get negative 4 pi over e plus 2 pi. And that is a transcendental number if I ever did see one. So that's it. Fun stuff. Enjoy. If you have questions, please send me an email.